Hello engineers and future engineers, I am Adriana A. Fernandez from DCPET 2-2. Today, let's talk about Mars Climate Orbiter Mission Investigation Board. I will share to you my reflection in this report case. Here we will tackle what is this report case all about, the issues and recommendations as well as its importance and my learning in this case. What is the report all about? On November 10, 1999, the Mars Climate Orbiter Mission Investigation Board issued its Phase 1 report. The study was developed to evaluate the failure of the Mars Climate Orbiter mission, which went missing in orbit on September 23, 1999. The study determined that accumulated errors were the root cause, also known as the small forces, as well as the contributing causes. These errors were created by operational methods and software that were not thoroughly examined, evaluated, or implemented. However, this case report also included many recommendations to increase the probability of success for future space missions. As I mentioned, the main issue is the MCO root cause, or small forces. The MCO-MIB has identified the failure to use metric units in the coding of a ground software file, which was used in trajectory models. The thruster performance data was reported in English units instead of metric units, causing the loss of the MCO spacecraft. Of 8 contributing causes. Number 1, undetected improperly modeled spacecraft velocity changes. Due to improperly modeled spacecraft velocity changes, ground software AMD data incorrectly reported impulse beat values in English units, leading to delayed use of accurate trajectory data. Limited observability of thrust magnitude and incorrect modeling of thruster effects perpendicular to the spacecraft's flight path exacerbated the issue, leading to an inaccurate trajectory estimation and mission failures. Number 2. Navigation team unfamiliar with spacecraft. The operation navigation team was unfamiliar with the spacecraft attitude operations, leading to increased navigation analysis to quantify an orbit determination residual error. The team did not participate in ground software testing, preliminary design review, or critical design review processing, resulting in a line-of-sight error. Number 3. Trajectory correction maneuver number 5 not performed. Due to concern and procedural constraints, the operation team did not fully analyze TCM5, prioritizing MOI maneuver timeline over TCM5 executions. There was also a lack of understanding among spacecraft operations and navigation personnel about TCM5's criticality and confusion and oversight regarding TCM5 scheduling for the EDL phase. Number 4. The system engineering process did not enough address the transition from development to operations. This led to inefficient contingency planning, a misunderstanding of crucial operational trade-offs, and communication issues among subsystems engineers. Number 5. Inadequate communications between project elements. The MCO and MPL projects were significantly impacted by poor communication between various teams, leading to mission failures. The operations navigation teams was isolated from the development and operation teams, causing knowledge gaps and decision-making issues. The lack of robust systems engineering support further isolated the team. Number 6. Inadequate operations navigation team staffing. Due to MCO loss, MPL had 3 navigators but only 2 were on board. 24 hour per day navigation staffing was planned for a brief period before MPL entry, descent, and landing, which was not feasible for a single MCO navigator. Number 7. Inadequate training. Inefficient training in the MCO project, including inefficient training for the Operation Navigation Team, the Small Forces Software Development Team, and the MCO team on the design, operation, ISA, end-to-end testing, and recognition of mission-critical small forces ground software. And validation process did not adequately address ground software, including the ineffective use of the software interface specification, inefficient end-to-end testing for small forces ground software performance, and incomplete or inefficient verification of specific ground system interfaces. How NASA addressed the issues. The following are the MPL recommendations that NASA provides to address the issue. In small forces issue, verify the consistency of units throughout the MPL spacecraft design and operations. Conduct audit for specification compliance on all data transferred between JPL and Lockheed Martin Astronautics. Ensure that units are used consistently throughout the spacecraft's design and operations. Conducting a software audit for SAS compliances on all data exchange between the JPL Operation Navigation Team and the spacecraft operation teams. Modeling of spacecraft velocity changes. Verify small forces models used for MPL. Compare prime MPL navigation projections with projection by alternate navigation methods. The board advises that the small forces models used for MPL be verified to ensure that the modeled forces are properly treated, including thruster activity utilized for attitude control and solar radiation pressure. Furthermore, various navigation techniques should be compared to the primary navigation method to assist in revealing any improperly modeled minor forces on MPL. Knowledge of spacecraft characteristics. Train the navigation team in spacecraft design and operations. Conducting team training on attitude subsystems and other factors affecting navigation accuracy. Face-to-face meetings with spacecraft development and operations teams are suggested. Trajectory Corrections Maneuver (TCM-5). Prepare for possibility of executing Trajectory Correction Maneuver number 5. Establish MPL systems organization to concentrate on Trajectory Corrections Maneuver number 5 and entry, descent, and landing operations. System engineering process. Establish a system engineering organization focusing on TCM-5 and EDL activities. Updating risk assessments for EDL and Mars ground operations. And reviewing systems engineering to ensure the MPL mission is ready for EDL sequence. Communication among project elements. Take steps to improve communications. Operations Navigation Team Staffing. Augment operation team with experienced people to support entry, descent, and landing. Augmenting operations navigation staff with experienced individual to support the MPL EDL sequence. Assigning a third navigator and identifying backup personnel for critical roles in case of an ill navigator. Also create contingency plans to ensure the backup of key personnel for mission-critical functions in any project area. Training of personnel. Train the entire MPL team and encourage the use of incidents, surprise, and anomaly processes. Training the MPL Operation Navigation Team in spacecraft design and operations, identifying mission-critical ground software, and promoting a mission safety first attitude, encouraging issue writing and anomaly generation. Verify and validation process. Develop and execute systems verification matrix for all requirements. Create a system verification matrix for all project requirements, including interface control documents. The MPL team should review this matrix at major reviews, requiring end users to sign off the ground, software application, and products for applicability and data transfer. Trajectory margin for Mars orbit insertion. Perform thermal analysis of thrusters, feed line heaters, and consider the use of preconditioning pulses. The board recommends enhancing data analysis procedures, implementing an independent navigation peer panel, and engaging the entire MPL team in TCM and EDL planning. Independent reviews. Conduct independent reviews on all mission-critical events. Ensure operation navigation discipline presence at major reviews. Involve subsystem specialists and implement a formal peer review process for mission-critical events, particularly critical navigation events. Contingency planning process. Re-examine propulsion subsystem operation during entry, descent, and landing. Contingency planning must be defined products developed, tested, and trained. A systematic assessment of potential failure modes is necessary for project contingency plans. The MPL team should establish go-no-go criteria for each scenario and poll operations team and subsystem experts. From development to operations. Increase MPL operation and navigation teams. Recall development team members. Consider co-location of JPL and LMA personnel, and review handoff from JPL operations navigation to LMA EDL team. Matrix management. Immediately include line managers in independently assessing and carrying out the remaining tasks to accomplish a successful MPL landing. Mission assurance. Assign overall mission manager. As soon as feasible, assign a mission assurance manager to MSOP. Science involvement. Involve the project scientists in managing the remaining MPL mission, including decisions in entry, descent, and landing. Navigation capabilities. MPL project personnel should challenge and question existing practices, while JPL top management should emphasize cultural change. Management of critical flight decisions. Plan and execute the remaining MPL mission with timely and disciplined decision-making. And lastly, analyzing what could go wrong. Construct a fault tree analysis for the remainder of the MPL mission. Perform a fault tree analysis for the MPL mission, follow up on results, and consider using an external facilitator if JPL lacks expertise. How important the knowledge and field of computer engineering in the space technology. Computer engineering is responsible for designing and implementing hardware and software systems that control spacecraft functions such as navigation, communication, and data processing. It is also involved in system integration and testing, which is crucial for every space technology mission. It identifies potential risks and implements quality assurance measures to prevent failures, including thorough code reviews, simulation testing, and validation processes. Also, computer engineering conducted a comprehensive investigation to understand the causes, identifying the errors, and learn from the mistakes to prevent similar issues in future missions. Furthermore, it is important for continuous improvement in both hardware and software design and implementation within the aerospace industry. Based on this case, as a future computer engineer, it is important to learn from these mistakes and take steps to prevent similar errors from occurring in the future projects. In this case, I learned various things such as understanding its historical context, the valuable lesson about the complexities and challenges inherent in space technology projects. It underscores the importance of meticulous planning, attention to detail, and adherence to established engineering principles. Also, learning clear project definition is crucial for stakeholder alignment and effective decision making. Future computer engineers should actively participate in defining requirements, objectives, and scope. In its concept of method of investigation, it serves as a blueprint for conducting thorough post-mortem analysis. Future computer engineers should familiarize themselves with investigative techniques such as root cause analysis, fault tree analysis, and simulation-based testing to identify underlying issues and prevent recurrences. In addition, this case serves as a sobering reminder of the far-reaching consequences of seemingly minor errors in engineering designs, implementations, and validation. Computer engineers or future computer engineers must approach their projects with a mindset of diligence, rigor, and attention to detail, recognizing that even small oversight can have catastrophic implications. The most essential lesson learned from this case are to ensure clear communication and standardization of units of measurement, to properly test and assess software, and to build a culture and collaboration and teamwork. By learning from past mistakes, future computer engineer may assist in ensuring project success and avoid costly failures. That's all for my reflection about Mars Climate Orbiter, Mission Investigation Board Phase 1 report. Thank you for listening.